We were looking at noise calculations in a circuit, and the example circuit that we took was this, where the transistor is biased at a given GM and it's in saturation region, and we have Vi. We saw that the output noise voltage is given by output noise spectral density is given by this expression, right? Okay. Now I want to represent all the noise of the circuit by a single noise source at the input, useful for many reasons, to compare with the input itself, and for modeling. When you have a number of noise sources in the circuit, you give the input output model just like a two-port model, but you also include noise at the input. Okay. So what will be the spectral density of this? So it's basically you calculate the output noise spectral density and divide it by the transfer function magnitude square. Okay. Because the spectral density of Vn times the magnitude square of the transfer function is the spectral density of the output noise. Okay. So what do you get that to be? Yeah. So you will get basically this this thing divided by GMRL squared. Okay. So you will get this plus 4kTRL by GMRL square, right? And this is due to the transistor, the first term, and the second one is due to the load resistor. Okay. So this is the voltage noise spectral density, and this is a very common representation. Okay. To define an input referred noise which has the same effect in a noiseless circuit as all the noise sources in the circuit. Okay. Now this input referred noise is not something that you see anywhere in the circuit, right? It's not something that you measure. Okay. It's a representation of all the noise in the circuit. Output noise is, of course, if you stick a noise measurement unit to the output, you will see that noise. Okay. Whereas the input referred noise is the noise which in a noiseless circuit which will result in the same output noise. Okay. So a couple of things. Firstly, this I won't go into details, but let's say you have any two-port with a number of noisy components inside, resistors, MOS transistors, and so on. Okay. And you can drive it with any kind of source, let's say. By any kind of source, I mean a source with any impedance. Okay. And you want an input referred noise representation for this situation, which will work for any kind of source. Okay. Now it turns out, I won't go into the proof of this, it can be proved from elementary network theory. Essentially, you calculate noise transfer functions from here to the output and then divide it by input square and so on. I mean divided by the transfer function square. You will need two sources, okay, to represent it correctly. That is, this Vn and In will be dependent on this network N. Okay. Once you represent it like this with an appropriate values of Vn and In, it will work for any value of the input. Okay. So this is the actual model of the network with noise. Okay. That is, the noise of all the components in the circuit is represented by this Vn and In. Now, let's imagine that the driving input is a perfect voltage source. Okay. What happens to ion? Current, it is short circuited. Basically, ion has no effect on the output. Only Vn has, right? So in such a situation, Vn is enough. If the input is a perfect voltage source, you can use only a voltage source to represent the noise. Okay. Similarly, if the input was actually a current source, what happens then? Vn has no effect because Vn in series with the current source is simply the current source. Okay. So if the input is purely a current source, the input referred current noise source is enough to represent the noise of the circuit. But if it is something in between, that is a voltage source in series with some finite resistance or impedance, or a current source in parallel with a finite impedance, you will need both. Okay. Now, we will not use this representation, for a complete description you need this, just be aware of this, and I will also put out some handout where you can show that this is required. Okay. Now, the slight complication with using this is that this Vn and In are a result of the same components in the circuit. Some combination. Each resistor will affect Vn in some way and In in some way. Okay. So, these two are not uncorrelated. This Vn and In actually have some correlation between them. Okay. Just imagine you had a single noisy component in the circuit, then Vn will depend on that noisy component obviously, and In will also depend on that noisy component, and the two will be perfectly correlated. Now, when you have multiple components, there will be some correlation to some extent, and you have to specify that also. So, even when this is specified, that's not enough, you also have to specify the correlation between them, and the calculation is not as simple as with two independent sources, right? When we had let's say a resistor and a MOS transistor, you calculate the output noise due to resistor, due to MOS transistor, and add up the spectral densities. But you can't do that with Vn and In. You can't calculate the output spectral density due to Vn, due to In, and add up the results. Okay. You have to also take into account the correlation. So that's why it's a little complicated and we will not use it. We will basically always get it to a form where the input is either a voltage source or a current source and use one of them, either the input referred current source or input referred voltage source. Is this okay? But it is incomplete, that you should be aware of. Is it okay? Now, I said this is the input referred voltage noise spectral density of this circuit, and the first term here is due to the MOS transistor. And in fact, sometimes you use the model of the MOS transistor we used is a parallel noise current source In, whose spectral density is 8/3 kT gm. Alternatively, you can also refer it to the input when you use a simple MOS transistor, a MOS transistor by itself, and that would be a voltage source whose spectral density is 8/3 kT divided by gm. Okay, these two are equivalent. You can use either one. Most of the time I use the current source model, but in some cases it may be easy to refer the noise of the MOS transistor also to the input. This is nothing new here. For a resistor also we use either a parallel current source or a series voltage source. Similarly here we have to use it in series with the gate. Okay. But once you know the representation of noise, everything else is easy, in that it is just like small signal calculation from the noise source to the output, and then noise from different components are uncorrelated. You add up all the noise spectral densities, okay, and then you can find the noise variance and so on. Okay. Any questions about any part of noise calculations we have done so far? Noise models or calculation? Yes. Yeah. What's that? None. None. I mean, meaning, see, basically, if you know this model, and let's say you did not know that it's even related to inversion charge, but you know this and circuit analysis, it's enough to calculate what you want. It's always good to know more stuff. But what I'm saying is that if I just showed you this model and then I and a small signal, you can calculate everything you want, right? Yeah. Yeah, correct. So basically, it's always, I mean, in any model, I mean, even in circuit models, right? So some things will work up to some extent. To what extent they work, if you want to figure out, you will know, you will have to go deeper into the science behind it. Okay. So in that particular case, I showed the inversion charge mainly to show that when VDS equals 0, it looks exactly like a resistor. And also that, yeah, it is in fact like a resistor. You have charges which are colliding with fixed atoms and so on. Yeah, I mean, I don't mean to discourage anybody from studying device physics, but I said to use the model, you don't need to know it. Okay. So let's continue this for a couple of other components. Essentially, the lossless components like inductors and capacitors don't have noise associated with them. And then we have the other type of transistor, which is the bipolar junction transistor. It is not used as widely as the MOS transistor these days. By the way, the noise model for NMOS and PMOS is the same. It's you will still get 830 kDGM. It is just that for the PMOS you have to calculate the GM appropriately from each parameter. That's all. Okay. This is the bipolar junction transistor. And you know the model of the bipolar junction transistor again by itself. So this is VBE. And in this case, we will consider only the active region where VCE is sufficiently large. Okay. Active region is where VCE is greater than some VCE SAT, which is also about 0.7 volts. It may be less. Okay. And you know the model for the large signal currents. Okay. This is again the 0th order model where Vt is the thermal voltage and Is is the saturation current of the MOS, so saturation current of the bipolar transistor. Okay. And interestingly, actually a MOS transistor also, if you operate with VGS minus VT less than about, let's say, 6 times the thermal voltage or so, what is known as the weak inversion region, it also has this type of behavior. Okay. It also has this exponential type behavior, and the mechanism of current is similar in a MOS transistor as in a bipolar transistor. Okay. So the current varies exponentially with VGS instead of being this square law. This square law happens only when VGS minus VT is sufficiently large, and the sufficiently large is basically more than 6 times the thermal voltage. The thermal voltage is how much? How much is the thermal voltage? 25 millivolts. Okay, so about VGS minus VT more than 150 millivolts or so, it will be in strong inversion. If you know that actually in a real MOSFET, right, according to the 0th order model, if VGS is less than VT, the current is 0. That doesn't happen. Actually, when VGS approaches VT, the current starts falling exponentially but it won't fall to 0. Okay. So in this case, basically, the noise of a bipolar transistor also can be represented as an additional current source, okay, from the collector to emitter, and the noise of that, the mechanism of this noise, it is known as short noise. So again, if you remember the physics of the bipolar transistor, you know that carriers are launched from the emitter and then they shoot through to the base and go to the collector. Now, the same thing happens in vacuum tubes and so on. Okay, but it's not as though, although you have a certain average current, it's not as though they'll all be, the flow of electrons is periodic. Okay, that is the timing of the firing of, or the arrival of electrons is some random distribution. Okay, and that gives you this short noise. Okay, so you have some average current and you have some fluctuations around it, and this is 2Q times IC, where IC is the collector current that is flowing from collector to emitter, and this is the electron charge. Okay. Now this can also be in the active region. What is the expression for GM of the bipolar transistor? IC by VT. What is VT? What is VT? What is the expression for VT? KT by Q. So this is the GM, right? So basically this can also be written as 2 kT GM. Okay. So we have like 4 kT times G in a resistor, 1/3 kT times GM in a MOS transistor, and 2 kT GM in a bipolar transistor. Okay. Now you have base current also, and there is an additional noise current source, which is the base short noise. Okay, and it has a similar expression. It's 2Q times IB. Okay.
BJT, why is the hybrid by model called hybrid?
I don't know what is the hybrid pi model. Usually this type of network, this is what is known as a pi network. What is the hybrid pi model? It is whatever this, and you have these capacitors here, right? And I don't know if it also includes a parasitic resistor. Yeah. No, I'm not talking about the RE, the parasitic resistance of the transistor. In that case, this is not exactly a pi. I don't know why it's called a hybrid pi model. So you have short noise. By the way, this also is, as you can see, these are also white noise spectral densities, in that the spectral density is independent of frequency, right? The same goes for the thermal noise in a MOS transistor. And when the MOS transistor is operating in this exponential type region, in the weak inversion region, the same expression applies. In that case, the noise spectral density will again be 2Q times ID, where ID is the current from drain to source. Okay. This is fine. So anyway, I mean, basically these are models, and if you have a circuit with bipolar transistors, you can put in the appropriate models and then see. Now, these models again, just like the small signal models that you would use for small signal equivalents, these also depend on small signal parameters like GM, right? Or here in this case, the total collector current IC. So if you have a situation where you have large signal excursions in the bias current, GM will also be varying with time. This especially happens with circuits in which you have periodic variations of GM or IC and so on. So then you have essentially cyclostationary type behavior where the noise, it's hard to define what the noise spectral density is, but that autocorrelation is periodic. Okay. So you will have to imagine the noise spectral density at each instant of time and then average it over a cycle and so on. Typically difficult to do it by hand, but the simulators take care of it. That is, what I am saying is with the signal GM itself will be varying. So the noise calculation has to take that into account. If it is small signal variation, it may not be much, but if it is large excursions, then it may be significant. But the simulators do take care of all those things. Okay. Now, just continuing with the noise models. In addition to, so if you look at I said that if the spectral density of this IN is a third kT GM. This is the thermal noise spectral density plotted versus frequency. If you measure the drain current of a MOS transistor and plot the noise spectral density, you will see that actually at high frequencies it will follow this, and at low frequencies it rises up at basically plus 10 dB per decade, which means it has the spectral density has a 1 by f type dependence. Okay. So this is what you would see. This actually you see also in bipolar transistors and even in resistors, but the magnitude is a lot more significant in a MOS transistor than in a resistor or in a bipolar transistor. Okay. Again, without going too much into the physics, the reason it happens is the following. This is not actually something that is, I would say, fundamental, but you can think of it as a result of some imperfections. So this is the MOS transistor again. The charge on the gate is balanced by the inversion charge plus whatever fixed charge you have and so on. Okay. So that's how you get the equations for the MOS transistor. Now, it turns out that these surfaces are imperfect and they trap some charges. Okay, they trap some charges and release them with some various time constants. Now, if you imagine that there is some extra charge that is trapped here, that has to be balanced by the gate charge. Okay, so those things, I think, again, if you have studied the physics of the MOS transistor, you know that it affects the threshold voltage. If you have a bunch of trap charge here, then that has to be balanced by the gate charge. That amounts to a shift in the threshold voltage. Now, this is also dynamic. If this process is dynamic, that is, if the charges are getting trapped and detrapped with various time constants, it's like you can again think of it as a time varying threshold voltage. Okay. So this flicker noise is a result of that. You will have a number of these traps which also have a wide distribution of time constants. Some of them release rapidly and then some of them hold it for a long time. And if you combine all of that effect, you will end up with this 1 over f type spectral density, which is known as 1 over f noise or flicker noise. Okay. Now this is a little bit process dependent. You take a MOS transistor from any foundry, at least long channel MOS transistors which obey this square law and so on, and you bias them at a certain GM, the thermal noise will be 830 kT GM. Okay, but it's not necessary that they have the same flicker noise. Okay, they can have widely varying ones. It depends on how nicely the surface is fabricated, etc., etc. Okay, and it's also different for NMOS and PMOS. And the way to model this flicker noise, you can either use a current source in parallel with between drain and source, or you can use a voltage source in series with the gate. Okay, so essentially you have to use one of these things, of course, not both. If you refer it as a voltage in series with the gate, it turns out that quantity is basically independent of the bias condition of the transistor. Okay, so it will be some constant, I will call it K 1 by F, okay, divided by WL. Okay, it is inversely proportional to the area. Again, intuitively, why it is inversely proportional to the area is if the gate area is large, you will have a larger number of traps, and then the trapping of some will average with the detrapping of something else, and then overall the effect reduces in a relative sense. Okay. So again, we don't need to get into the physics of all those things. So if this is the model for the gate referred flicker noise, what will it be for this? What will be the model for this? It will be basically times GM square. Okay, so GM square, and you know that the expression for GM, there are various expressions, but let's say you use this expression, you will get basically some other constant. This mu Cox and all those things can be absorbed into some other constant, K prime 1 by F ID by L square. Okay, because the W goes away with the other W, right? I am basically multiplying this by the square of this expression, and this W goes away, you have L square in the denominator and ID also in the numerator, and you will have some other constant which is this times those constants. Okay. So this again is a useful expression. This is relevant when, let's say, you are realizing a current source. So this means that if the MOS transistor will have noise. If you make a MOS current source, like in a current mirror and so on, it will also have noise, and it will have flicker noise. Now what this expression is saying is, let's say you want a less noisy current source, what do you have to do? Area. Length. If you are looking at only the current source, right? If you want a 100 microampere current source and you want less flicker noise from it, you can see here this depends only on the current and L square. So the only way is to make longer transistor. Okay. So that's why these low noise, high precision circuits end up using longer channel transistors. Now this again is a trade-off that you will see more in detail in IC design, analog IC design if you are taking it. You always have a trade-off between precision, power dissipation and bandwidth. Okay. So for high precision you should make everything big. Okay. Then if you have two identical devices, they will be matched very well and all that stuff. On the other hand, if you make everything big, the parasitic capacitors will increase. So that means that the circuits will become slower. Okay. Also, to charge these parasitic capacitors at a given rate, you will need higher currents and so on. You may have to increase the power dissipation. Okay. So these things are contradicting trade-offs that you will have to fight with. What's that? Huh? Pardon, what is that? Oh yeah, of course. Actually, I forgot the most important part of this. Yeah, it is inversely proportional to F, of course. and this frequency where the flicker noise density equals the thermal noise density, it's known as the 1 over f corner, f1 by f, or the flicker noise corner. This is also called a flicker noise. Okay. Now this again, nothing special about it, it's another kind of noise. You add this source, do your usual analysis and so on. But sometimes it can you can end up with difficulties in that this 1 by f, right, this expression, you can integrate this as long as the lower limit is not 0. Okay. So if you integrate this, you will get log f, and then you can't have a lower limit of 0. So you will have to impose some lower limit for integration that usually comes from the context. But otherwise, I mean, this noise is the same as any other noise. So one thing to keep in mind is if you are interested in low frequency circuits, right, for audio or even instrumentation type stuff, this flicker noise can be very significant. The flicker noise can be a lot bigger than thermal noise and can overwhelm the picture. Okay. You have to either use very long transistors. That may or may not be possible, because you can imagine that if you want to reduce this flicker noise density by, let's say, a factor of 2 or 4, you can maybe increase W and L by factors of 2, and that's okay. But if you have to reduce it by factor of 1000, you can't realistically get that by increasing W and L. You will have to resort to some other circuit techniques which will fix that problem. Okay. Any questions? Okay. So this is about the circuit models. In summary, I mean, by the way, I mean, if you find cases where the resistors have significant flicker noise, all you have to do is add another spectral density term that's proportional to 1 by f. That constant will be given by the process manual. Okay. Similarly for bipolar transistors. It just turns out that in a bipolar transistor also there is flicker noise, but the flicker noise corner frequency is much lower usually. So it is not as significant as in a MOS transistor. And also one sort of good thing for us with serial links, as long as we are dealing with very broadband circuits, I said our focus is on making very high speed links, right, where we are talking about frequencies of gigahertz and so on. So flicker noise is less of a concern. If you are focusing on audio and instrumentation and things like that, it is like really big concern. Okay, because we will be operating usually at frequencies that are well beyond the flicker noise corner, and thermal noise is the dominant noise in our case. Okay. There is no fixed number. So this flicker noise corner, as you can see, it depends on L. Okay. So now if you use the minimum length transistor in a given process, it also depends on this thermal noise. Okay. So it depends on the bias condition. But overall, if you take the minimum length transistor in a given process, as the process geometry has decreased, right, as it has gone from, I don't know, 180 nanometers to 130 down to 65, now even below 10 nanometers now, this flicker noise corner goes on increasing. And then sometimes, like with some process, it actually reduces. But in really modern processes, this corner can be as high as like hundreds of megahertz also, okay, or gigahertz, but it depends on the size of the transistor. Okay. And also one more thing is, typically it is better for, it is lower for PMOS than for NMOS, but not universally. I mean, there are some processes in which they are about the same, and also some processes where NMOS has lower flicker noise. Yes? They are not different for our type of first order calculations, but the flicker noise may be lower in that way. So far as I know, they are the same. All the differences come in the engineering. The widths are, you cannot have arbitrary widths because of the fin and things like that. Okay. And also it just turns out that you will have better GM by GDS and things so on. So, but those are like parameter differences, but the model itself, I don't know if there is a difference. So FinFET is basically the same thing, like folded up. I don't know if everybody has heard of this, but so this part here, this is where the gate controls the charge, and this charge is available to you. Okay. And then, so this is the lengthwise dimension. Okay. And this is the width. Okay. And the current flows from, if this is the drain and source, the current flows like this. Okay. Now if you look from this side, the cross section again simply looks like this. Okay, you will have channel here. In a FinFET, what has happened is, I mean, this is the width, this is this view. Okay. In a FinFET, to get effectively like, so if you go on increasing width, like many other parasitics and so on goes on increasing. Now as they have shrunk the geometries, it's become like more and more difficult to do that while retaining control of the gate. Over the channel. So this fin is basically, this gate is folded up like this, and this is the insulator part, and essentially it is like gate which is surrounding the channel, so it has a greater control. And then now there is the all around surround also, so you have gate and then the channel inside, and I think you have even better control over the channel. Okay. I mean, that's actually quite complicated, and I have not done it also, but I mean, there are rules, but the rules are a lot more complicated. So these are about the noise models of the components, and this is basically good enough for us, right? I mean, we use the noise models and then use small signal analysis to calculate the output noise spectral density, and from that we can go on to calculate anything. It's either the output noise variance or the input referred noise spectral density, anything that we want we can calculate from that. Okay. All we need to know is the right noise models. This is fine. And along the way we also drawn some conclusions, like if you have an RC, if you have a capacitor C, you will end up with a noise of at least kT by C on it. And similarly, what was that? You can refer the noise to the input, and if you want to reduce the thermal noise in a circuit, essentially you have to increase the power dissipation. Okay. So the noise scaling and so on I haven't dealt with. Let's see, if we have time we will do that. And in case of MOS transistor, you will also have flicker noise, which can be reduced essentially by making the device larger and larger. Okay. Any questions about any of this stuff? No, there is no correlation. No, correct. It's because of some completely different reason, right? So the flicker noise is because of the charge trapping and detrapping. Okay, whereas the thermal noise is because the charge carriers will collide with the fixed atoms in the lattice. Okay, so you can think of the flicker noise modulating the number of charges available. Okay, but the two noise processes are not correlated. Okay, so you just add up the spectral densities. Finally, the current is only due to the inversion charge, right? Inversion charge movement. So eventually, all the noise will affect that movement, but that doesn't mean they are correlated. The processes are uncorrelated. Anything else? So let's say I have an oscilloscope and then I connect a 100 kilo ohm resistor to it. Just a 100 kilo ohm resistor. Okay. What would I see on the screen? Okay, I'll see some zero mean noise. Okay. What will be the size, amplitude or whatever? No, it will be random of course. But I mean, whole of last week I have been saying that yeah, it will be random, but you can specify the size in some way, right? Huh? No, I mean, I want to know what I see on the oscilloscope. Oscilloscope displays the waveform versus time, right? So what is it that I'm going to see? 3 sigma. Yeah, okay. So essentially you have a Gaussian distributed noise, and then there is no, the amplitude is actually infinity, right, of a Gaussian distribution. But let's say that 3 sigma is, beyond that you see it only once in 1,000 times, so you really actually cannot see it on the oscilloscope, so let's forget that. And what is the sigma value? Huh? So 4 kDr times the terahertz limit, is that the... Yeah, so it's the oscilloscope's bandwidth, right? So the oscilloscope will have some bandwidth. Let's assume it's an abrupt filter. So basically you will see 4 kDr times the bandwidth. This is the variance of that noise. So how much will that be? So let's say if the bandwidth is 100 megahertz. What is the noise spectral density of a 100 kilo ohm resistor? 4 nanovolts per root hertz. No. Huh? 40 nanovolts per root hertz. And this has to be multiplied with how much? Square root of the bandwidth. Okay. So how much is that? What is the square root of the bandwidth? 10? Okay, so what is sigma n? What is it? Yeah, it's 400 microvolts or 0.4 millivolts. So basically I will see something. If I plot the distribution, I will see this with sigma of 0.4 millivolts. And if you look at it as an oscilloscope waveform, maybe you will not see much beyond 3 sigma because it happens like very rarely, right? So then maybe you will see something which has a pulse of about plus minus 1 millivolt width. Okay. So in reality there will be bandwidth limiting somewhere. Okay. Although we use the thermal noise models with which are white and extend to infinite frequency, there has to be band limiting somewhere in the circuit or in the way you interpret the result. It will be somewhere. Okay. So depending on that you will see a certain noise variance. In this case it will be the oscilloscope bandwidth. Okay. And if there was a parasitic capacitance here, I mean I assume that this 100 kilo ohm resistor has no parasitic capacitance and it goes to the oscilloscope. Oscilloscope reads the value across the 100 kilo ohm resistor but with its own bandwidth limitation. But if I had, let's say, 1 picofarad capacitor across this, what would happen? What would you see? The bandwidth would be limited by this one. In this case, I mean if it's 100 kilo ohm and this, you can calculate it and see. If it is not limited by this one, it will be limited by the oscilloscope bandwidth. So you have to also see where it gets limited. In this case, because this 100 kilo ohms times 1 picofarad, what is the bandwidth associated with this? How much? 10 megawatt. It's not hertz. Radians. So it's basically 1.59 megahertz, right? 10 megaradians per second. So the limitation due to this is the dominant one. So what do you see? What was the integrated noise across 1 picofarad? Yeah, how much was that? Calculated it right few pages before. 63 microvolts. So you will see a smaller noise because it's band limited to a smaller one. Okay. So what I am trying to say is that sometimes we will calculate spectral densities, and in that circuit model the bandwidth limitation may not be obvious, like the common source amplifier I gave you, right? But in reality it will be limited either by its own output parasitic capacitance or the bandwidth limitation of whatever circuit is following it. Okay, it has to be. So now we have hopefully a reasonable working knowledge of noise models. We went into some very basic concepts of random processes and so on, but essentially most of our calculations will involve applying the noise model, calculating the spectral density. But you do need to know what that spectral density relates to, right? Just like when you do frequency domain calculations, you need to know how it relates to the signals that we see in the lab in the time domain. Similarly here also you need to know. So that's why we went into this concept of autocorrelation, etc., etc. So the size of the noise, so to speak, is specified by the variance, and that you can calculate from the spectral density. Okay. So from here on, we will look at some other details with respect to noise, and then go back to our original problem, which was you want to transmit bits, and there will be some errors in that errors are due to noise. We were calculating how much that is, etc. Okay.